In order to determine the stress at each corner of the member subjected to a moment of 850 Newton meters acting along the YZ plane, making an angle of 30 degrees with respect to the Y axis, as shown in the figure, we can start by first writing our expression of the normal stress that is caused by the bending moment. So, our expression is given as sigma equals to mc over I, where sigma is the normal stress, m is the moment that is acting on the member, c is the distance, or in other words, the perpendicular distance from our neutral axis to the point across which we are going to calculate the value of a stress. So in this case, since we want to sketch the stress distribution, we are looking for the stress at each corners, that is at point A, B, D, and E. Next, our value of I is our moment of inertia, that is a geometric property. So to start, let us first figure out our moment. Since the moment is making an angle of 30 degrees, so let's first resolve it along the y and z axis. To do that, since it is making an angle of 30 degrees with respect to the y-axis, the component along the y-axis can be calculated by taking the cos function. So 850 times cos 30 give us our value of 736.12 Newton meters. Now, in this case, the component of the moment acting along the y-axis is making our counterclockwise moment. Similarly, by taking the sine 30 function, we can project our moment component along the z-axis. So taking 850 times sine 30, we get the value of 425 Newton meters. Now, in this thing again, it is making our counterclockwise moment with respect to the positive z-axis as shown in the figure. Once we have the value of moment, let's first calculate our moment of inertia. That is our geometric property. For a square or a rectangular shape, it is given as 1 over 12 bh cube, where b is the base since we are calculating with respect to the y-axis. So b value will be a distance from a to d, that is equals to 0.25, whereas the h value, that is a perpendicular distance, in this case a distance between d and e, also equals to 0.25 cube. Simplifying, we get the value of I y as 0.3255 10 raised to power negative 3 meter raised to power 4. Next, let's go ahead and calculate the moment of inertia about the z-axis. Again, the formula is the same, 1 over 12 bh cube. Now, value of b in this case is a distance from D to E that is parallel to the z-axis, that is equals to 0.25. Similarly, the h value will be a perpendicular distance, in this case a distance from B to E, again 0.25. Simplifying, we get exactly the same value of Iz as 0.3255 10 raised to power negative 3 meter raised to power 4. Next, let's go ahead and start writing our stress equations at each one of those corners, starting with our point A. So for sigma A, it has an effect of both my and mz acting on it. So each one of them will be contributing in the stresses. So let's go ahead and start with my. Now, in this case, the my, since the moment is acting in the counterclockwise direction along the y-axis, so it is causing a stress in the compression at point A as shown in the figure. That's why I have the value of m as negative. So negative 736.12 times c, that is the perpendicular distance from the y-axis to point A. In this case, that is equals to 125 millimeters. That's why we have represented as 0.125 divided by I y. Next, I have a component of mc that is also going to create some stresses at point A. Now, in this case, if you look, because of our counterclockwise movement with respect to the positive z axis, the effect at point A is basically in tension as the arrow is going upward from point A and going into point D. So the region from point A all the way to the z axis will be experiencing the tensile stress. That's why I have positive 425 times 0.125. That is again the distance from our z-axis to point A divided by the value of Iz. That is again 0.3255 10 raised to power negative 3. Simplifying, we get our value of sigma A as negative 282.68 kilopascals plus 163.21 kilopascals. That is equals to negative 119.4 kilopascal. Here the negative sign is indicating that the stress is acting at point A is in compression. Next, let's move to point B, and we will do the same process, seeing the effect of both My and Mz at point B. Starting with our My, since the moment is making a counterclockwise direction with respect to point Y, our stresses at B is will be in the upward direction or in tension. That's why I have positive 736.12 times the perpendicular distance from Y to point B. Since it is a square, so this distance still remains 0.125 divided by the value of Iy. Next, for Mz, here you can observe that in this case again at point B, it will have a tensile effect based on the rotation of the moment happening. So we are adding 425 times 0.125 divided by the value of Iz, that is coming as 445.22 kilopascals. Next, let's go ahead and look at point D and again repeat the process of looking at the effect of My at point D and Mz at point D. Now, key thing, we just have to make sure that we have the correct direction. Now, if you look at the direction of our moment My, it is counterclockwise direction and our arrowhead is going inward towards point D. Since for this My moment, y-axis is the neutral axis and a distance from y-axis towards point D, we have compression stresses, where the distance from y-axis to point E we have the tensile stresses. That's why I have the value of sigma D equals to negative 736 times the c over I y. Next, if you look at Mz, again the arrowhead is going inward toward the section where our point D is acting. Again, we have the compressive stresses. That's why we have a negative term. Now, adding both of these terms, we get our value of negative 445.22 kilopascals. Finally, our last point E, in order you can see the effect of My is positive in this case, as the tail of the curved arrow head representing the moment is in our quadrant where E lies, whereas the effect of Mz is negative because the arrowhead is pushing point E inwards. That's why we have the compressive effect. So our term will be negative 425 times 0.125 over Iz, that is 0.3255 10 raised to power negative 3. Simplifying, we get our value of sigma E is 119.4 kilopascals. Now, once we have all the values of stresses at the corner, the next thing that is being asked in the problem is to sketch the stress distribution. Now, to do that, First of all, we just list down the stresses at each one of the corners. In this case, sigma A is negative 119 kilopascal, sigma B is 445 kilopascal, sigma D is negative 445 kilopascal, whereas sigma E is 119 kilopascal. So to draw this distribution, let's go ahead and first draw our square and identifying the corners A, B, D, and E, and then identifying the value of a stress at each one of the corners. Now, one thing to keep in mind, the negative sign is just indicating the direction. So while we are drawing this thing, 119 value at A is going to represent the magnitude, while the arrowhead pointing downward is showing the direction of the stress. In this case, downward direction is representing the compressive stresses. So let's do this for each one of the corners first. Since at point B we have a positive value of 445, that's why my arrowhead is pointing in the upward direction. Whereas at point D, I have the value as negative 445. So my arrowhead is going to point in the downward direction. That is also representing that the stresses at point D is in compressive mode. Finally, we have point E, where I have a tensile stress of 119. So my arrowhead is pointing in the upward direction. Now, once you have identified stresses at each one of the corners, next we have to develop the profile. So if you observe the line segment DE, at point D, I have compressive stresses, whereas at point E, I have tensile stresses. It means that there is a conversion taking place somewhere on this line segment from the compression to tension. We need to identify that point, because wherever that transition is happening, that is identified as the neutral axis for the members, because we know for a neutral axis the stresses are equals to zero. Now to do that, we can utilize the interpolation function, basically identifying our value of y1 and y2 as the stresses and x1 and x2 as the distance along the line segment DE. So in this case, I have given the value of y2 equals to negative 445, whereas y1 is positive 119. X2 in this case I have taken as 0 as a reference point at point D, whereas our x1 is 250 because that's the thickness of the member, whereas the value of y is equals to 0 because that is where the stress value is equal to 0, our neutral axis, and x is the variable that we are trying to identify. So while we perform this interpolation, the value of x is coming as 197.3 millimeter. So a distance of 197.3 millimeters, our value of stress is equals to 0. So to draw the profile, basically from 445 become all the way to 0 and then go back up to 119 kilopascals. So we can draw the profile on the figure. Now, if you look at the line segment from B to E, both values are in tension. So we know there is no neutral axis going to be present within the line segment there. Similarly, if you look at the line segment AD, both the values at the extremes are in compression. So again, we won't have the neutral axis passing through this line segment. However, we will have a neutral axis that is going to pass the segment AB, because at point A we have the compressive stresses and at point B we have the tensile stresses. Now if you look, the stresses at point A is identical to stress at point E. However, the direction is opposite, whereas the stress at point D is same as point D. The only difference is the direction. So our value where our neutral axis is going to cut our line segment AB will be at a distance of 197.3 millimeters as well, but this time measure from point B as shown in the figure. Next, you can go ahead and draw the arrowheads identifying the direction of the stress distribution acting on the member.